All right, everyone. Hello, hello. We're going to go ahead and get started. All right. Hello, and welcome to each one of you here at School for Poetic Computation in the West Village of Manhattan or watching online. Thank you all for your presence, physical or remote. Peace, love, and blessings. My name is Nabil Hussain, and I organize today's event, Mathematics as a Religious Experience, along with my indispensable co-organizers, Zainab Aliyu and Lauren Gardner. I'd also like to acknowledge my co-organizers from the first iteration of this event last year, Nisha Tothong and Matt Jacobson. Then, in February 2019, we had more lessons and activities, but no sermon, which is what I really wanted to bring this time around. I'd also like to acknowledge Mirabai Knight, who is providing live captioning, and Bamani McClendon, who is working the live stream and recording, for their contributions to this event and its documentation. Thanks also to the artists showing work in the other room. Once again, Nisha Tothong and Matt Jacobson, last year's co-organizers, along with Sean Katangai and Keng Karna. Sorry if I mispronounced anyone's name. So I work to organize mathematics as religious experience for many reasons. One of which, the most obvious or straightforward from when I first conceived the notion back in 2018, is that I am a religious believer in math. It's not something that I've been in the habit of bringing up in every setting. I'm keenly aware it may be a strange thing to believe, a little out there, taking long to explain or discuss. I believe that if there are many or infinite universes, through black holes or wormholes or wherever, there could be different laws of physics, now or in the past or in the future, a faster or slower speed of light, strange forms of life. But no matter what is or has been or will be different in this or any other universe, I believe that 2 plus 2 is still 4 and 7 is still a prime number. Of course, there's no way I can prove that. I'm not confident I could convince you if you don't already feel it, though I am going to try. Maybe my words will fail to capture my feelings. Maybe they don't even make sense. But I know it. I'm more certain of it than I am of my name or my address. I don't regard it as having been my choice to know, to feel that there is a deep governing structure and harmony throughout the boundless universes. I don't consider this knowledge to be scientific or historical or in accordance with my other ordinary ways of knowing the material world. This is why I describe my belief as religious. Mathematics is the one and only thing that I've been convinced is beyond the material. I don't believe in a personal God or in revelation or in miraculous divine intervention in any traditional sense. Yet I draw on these types of belief for comfort, inspiration, and metaphor as I explore mathematics as a unifying theme connecting literally everything. I will share as much as I can of what I've learned of these matters in the short time I have with you all today. So some of the things I will say to you may sound like strange things to believe, but hey, you know what? Why not? All right, just go with it for like an hour if you haven't before. Seems relatively harmless compared to a lot of things that people believe, right? What could be wrong to regard mathematics prayerfully, to recognize something sacred in numbers and geometry and infinity and generally just all types of abstraction? For all the differences that distinguish them, many people have been united in this recognition for thousands of years in countless cultures across history. Maybe you believe in a God that created this structure along with much else. Maybe you don't. Maybe you think of yourself as familiar with much of this. Maybe not. I wouldn't doubt that many of you listening have far deeper mathematical and spiritual knowledge than I do myself. But no matter where we each begin from, I invite us all to go on a journey together. I couldn't tell you exactly when or where this journey began for me. Having worked in elementary school education before, I can tell you that very young children already have what is called number sense. I know as well that non-human animals also display evidence of number sense. It wouldn't surprise me to learn that plants also have some sort of number sense too. They're actually very sensitive and very perceptive. How much mathematical knowledge is inborn or empirical or intuitive? How much is uniquely human versus truly universal? And what is even the difference between these categories? I consider it unnecessary to answer. What I would like to begin by sharing with you all is a mathematical proof I learned as a teenager that completely blew my mind and played a large part in my budding interest in these topics and my decision to study mathematics in college. It is an argument that some infinities are larger than others, credited to the 19th century mathematician George Cantor, though I am not alone in believing it has older roots, which I will discuss a little bit later. But before I can say why not all infinities are the same size, first I have to say, what is size? So I want to be clear that proof-based traditions of mathematical inquiry are not coterminous with mathematics as a whole. However, I do consider them to be a very important source of knowledge. Characteristically, we begin with some definitions or assumptions or axioms, and then proceed to transform them step by step according to logical rules. If the assumptions are valid, and the reasoning is valid, then the conclusion must also be valid. It's worth noting that people may disagree not only about what assumptions make sense, but also about what logical rules should apply. There are actually many different logics to choose from. Besides classical logic, there's fuzzy logic and modal logic, ternary logic and intuitionistic logic, which actually wouldn't allow some of the arguments that I'm going to make. The level of agreement among mathematicians is quite remarkable compared to members of other disciplines, but it is still not uniform. But let's just get into it using classical logic. So what is size, or cardinality? I'm going to use the two terms synonymously, and speaking specifically about the cardinality of sets, where a set is any collection of objects. I could refer to the set of all my fingers and say that it has cardinality 10. And one way to see that it has the same cardinality as the set of all my toes would be to count both. But that's not the only way, and I'm not going to take off my shoes to prove it to you. All right, so suppose that you're helping prepare for a large meal. Someone else has already set out a bunch of plates at some really long table, and you're walking around with a basket of forks. Of course, there's no need for you to count the plates in order to know that you've put out the same number of forks. You can just place one fork next to each plate. This type of one-to-one correspondence is how we will define size or cardinality. Clear? Yeah. Two sets have the same cardinality if they can be put into a one-to-one correspondence or a bijection. That's our definition or assumption or axiom, backed up by an intuition that I hope you share. And here's a visual that might help someone. So we have here a little, sorry, let me just. So we have here an image that shows some of the different types of maps or functions or relationships that can exist between sets. So this one up here on the top left is what we call a bijection or one-to-one correspondence. So you can see that in this set over here called X, it has 4 elements, 1, 2, 3, and 4. In this other set over here named Y, we have elements D, B, C, and A. And there's a one-to-one correspondence that we can establish between these two sets, like this. Okay, this isn't the only possible correspondence. We could have sent 1 to B and 2 to D. There's other ways that we could have done it. But this is one way to do it. Okay, so it's called bijective because it's both injective and surjective. So here's just some other weird mathematical terminology that you might be familiar with or you might not. Okay. So there's always more than one name for everything in math, even just in English, let alone in other languages. But just to go over just some of the differences between this. So this map or function on the top right is what we call injective, or sometimes it's also referred to as into. And intuitively, like you can think of this, you can think of this terminology as coming from the fact that this set on the left kind of fits into the one on the right. Right? It's not any bigger. It could be the same size or it could be smaller. And this one down here at the bottom left, we call surjective or onto. Right? We say that we can kind of fit it onto this. It's at least as big. Okay? It could be the same size or it could be larger. And then this map, this final function on the bottom right here is a non-example, where we see 1 and 2 are both mapping to the same element. So it doesn't have that one-to-one correspondence because looking at this letter D, we don't know kind of how to go backwards, so to speak. And it's also not onto because it's not large enough, so to speak. It can't cover that set, kind of intuitively speaking. Okay. So normally when we're dealing with finite sets like this, right, with just a number of elements that we can just kind of get finished with counting, of course, taking away any element is going to result in a smaller set. But perhaps surprisingly, that's actually not true when we start to deal with infinite sets. Suppose that we had all the natural numbers, which I like to count 0, 1, 2, 3, and so forth. Some people like to count 1, 2, 3, 4, and so forth. I like 0. Either one is fine. And again, just as a side note about some of the philosophical issues that come up, there are some people, at least since Aristotle and Kronecker and some other mathematicians, who wouldn't like the idea of having an infinite set. They would disallow the idea of having a completed or an actual infinity as opposed to a merely potentially infinite process. But personally, I'm cool with having infinity, so let's just keep going. Okay. So suppose that we have the set of all natural numbers, 0, 1, 2, 3, and we just take away the first few. and we count 3, 4, 5, 6, then we're not actually going to be left with any less than we started, right? We're still going to be able to keep counting forever in each case. And so this might be surprising that you could take away some elements and not be left with any less than you began with. But not only could we take away a finite number of elements and be left with the same amount that we started with, we could actually take away an infinite number of elements and still be left with the same number that we started with, right? Because there's an infinite number of odd numbers. Suppose we took away all the odd numbers from all of our counting numbers. There's still going to be an infinite number of even numbers that are left. Right? So we can put these two sets into one-to-one correspondence. 1 will map to 2, 2 will map to 4, 3 will map to 6. In general, x will map to 2x, and we'll put them into a one-to-one correspondence, showing that these two sets are actually the same size. But of course, if we took away all of the natural numbers, we would be left with nothing, the empty set, which has cardinality 0, the unique set that has no elements. So already we kind of see how infinity kind of messes with a lot of our natural intuitions. Like we can't really say infinity minus infinity equals 0 or infinity minus infinity equals infinity. We kind of end up with like a kind of whichever result depending on exactly what we're doing. So we're going to need some other set of rules. Okay? But just to keep bending your mind maybe just a little bit more. So this argument, which is due to this mathematician, George Cantor, is a kind of a diagonal argument. Okay? So what we have here is the set of rational numbers, right? The set of ratios where we just take one natural number and divide it by another natural number. And so the integers, or the counting numbers, or the positive integers that we were just looking at, are just on this one column to the left, right? Anything divided by 1 will just be itself. And then we kind of have this huge square. And so it kind of seems like there should actually be quite a lot more rational numbers than counting numbers, right? If we just have this one column of, that represents the other set, and we kind of have this huge square. It kind of seems like it should be infinity squared, which seems like it might be a lot larger. But actually, we can put these two sets of natural numbers and of rational numbers into a one-to-one correspondence by just going around in this very simple way, right? We start in the top left corner, we go down, kind of go up into the right diagonal, and then go over. And in tracing this pattern along all the rational numbers, we can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And you can see that we're not going to miss any of them by following this pattern. So we can actually put an infinite set into a one-to-one correspondence with a proper subset of itself. We can actually count the rational numbers using just this one tiny subset of them. Okay? So this might be a little out there. Might seem a little weird. But even though I'm doing all this weird stuff, I've really only showed so far infinities that are all the same size, right? I'm showing how infinity is breaking our intuition, but what I haven't done is what I said I was going to do, which is show that some infinities are bigger than others. So let's go ahead and come to that. So this proof is what we call a proof by contradiction. We're going to assume that we're able to create a list of all of the real numbers, the decimal numbers, and then we're going to see how that assumption fails, how that actually doesn't work. Okay? So we actually don't even need to say that we have a list of all the real numbers in the world, all the decimal numbers that could possibly exist. But suppose that we just had a list of all the decimal numbers that are between 0 and 1. Okay? So you can see that on this right-hand side here, that it's all 0 point something, some really long list of numbers. This list of real numbers is not in any particular order. I don't know if any of these numbers look familiar. They're all just kind of weird random numbers. But I'm saying suppose that we had a list of all of them. Okay? Suppose that we had a list of all the decimal numbers that there are. And I'm saying, okay, we're going to put them in a list, and we're going to put them in a one-to-one correspondence with a set of natural numbers that we were just looking at. And what I'm going to do is show that this list actually can exist in one of the simplest ways that you could actually imagine. We're going to go down this diagonal again. And I'm saying, okay, since this first number is a 2, I'm going to pick 7 as part of my new number, just because it's not 2. It doesn't actually matter what it is as long as it's not 2. Okay? The second number is a 9, so I pick 4, just because it's not 9. The third number in the third decimal place has a 3, and so down here I pick 6. And by just going down the diagonal in this very simple way, I'm going to create a new number which doesn't appear anywhere on the list. It's going to be different from the first number in the first place, from the second number in the second place, from the third number in the third place, from the fourth number in the fourth place, and in general different from the nth number in the nth place. So just by going down the diagonal in this way, we're going to create a new number, which is nowhere on the list. But our assumption at the beginning was that we had every number on this list, and then we were able to just completely contradict that assumption in just this very simple way, which shows that our original assumption actually makes no sense. It's not actually possible to put all the decimal numbers, even just between 0 and 1, into a list. So we refer to this infinity on the left, the set of natural numbers, as countable, and we refer to this infinity on the right, the set of real numbers, as uncountable. Uncountable. And one thing that's really interesting about this argument as well is that we did this just for the numbers between 0 and 1, right? We actually could have done this we could have started somewhere else. Like, let's say that I wanted to do it for the numbers between 0.1 and 0.01. We could have just started here. We could have just started further down and applied this exact same argument to show that there are actually more numbers, more decimal numbers, or what are called real numbers, which is a terrible name, but it's a name that exists. We can actually show that there's more real numbers between any tiny interval that you can imagine as there are natural numbers counting from 0 up to infinity. All right? Okay. So one of the things that is really interesting, I think, about this argument is some of the correspondence that you see between some of the ideas that this 19th century mathematician George Cantor did with some ancient art. So what I have on the right-hand side here is a reproduction of a column that appears somewhere in ancient Egypt. I actually forgot where, but somewhere in ancient Egypt. And so this image on the left is an image of what we call the Cantor set, where you start with just a line segment. We can just say that this is of length 1, and then we take away the middle third, and then we take away the middle third of each of the ones that is left, and we kind of keep proceeding through this whole process infinitely. And you can see kind of the resemblance between that and this image that we have on the right. And in this way, we're going to end up with an infinite number of points, right? We're not actually going to end up with any fewer points, so to speak, because it's always going to remain this uncountable infinity, even as the length of all these little pieces added up kind of proceeds towards 0. And it's worth noting, one of the reasons that I think that some of these ideas have much older roots than George Cantor is because George Cantor's, I think, uncle, one of his relatives was actually an Egyptologist who studied these things. And I believe that he received some inspiration from that kind of cultural transmission. Okay? So there's a lot more to say about infinity. There's even more infinities. And then now that we know that there's different sizes of infinities, we could ask, like, which infinity characterizes how many infinities there are. And it turns out to be like a really big infinity, bigger than all the other infinities. But before we go too deep down this whole rabbit hole, I just want to pause for a minute and just ask, like, are you convinced? So I find this argument convincing. It's okay if you don't. And so I don't know how many people used to read Calvin and Hobbes comics or still do, but I used to read a lot of these comics as a kid, and this is a really great one that actually Matt shared, I think in 2018 or 2019 in the SFPC Slack. So we have here this young kid, Calvin. He's talking to his stuffed animal, Hobbes. When other people are around, Hobbes is like a stuffed animal, but when Calvin's the only one, then he'll like talk as like he'll talk and like stuff like that. And so Calvin is saying to Hobbes, I don't think math is a science. I think it's a religion. Hobbes is like, a religion? Calvin says, yeah, all these equations are like miracles. You take two numbers, and when you add them, they magically become one new number. No one can say how it happens. You either believe it or you don't. This whole book is full of things that have to be accepted on faith. It's a religion. Hobbes is like, in the public schools too. We should call a lawyer. And Calvin says, as a math atheist, I should be excused from this. And so I think, a lot of people don't believe in math. A lot of people would say that this argument that I've made makes no sense. There must be something wrong with it. Were you talking about where all these infinities come from? How are you just holding all this? And it's okay if you don't believe. I do want to share some of this knowledge or belief. But yeah, I mean, I don't consider math to be a missionary religion. I believe it governs all of these things, whether anyone believes it or not. And, but yeah, I guess during this whole talk, lecture, sermon, whatever it is, I do want it, for those of you who are here in this room, for it to just be a little bit of a conversation. And so before I go on, I just want to just take a moment to just open it up and just ask if anyone has any questions or just comments about, like, what did we just do with all these weird infinities?
So you said, like, we presented the second kind of the angle argument. And you said the real numbers are kind of uncountable, the natural numbers are uncountable, right?
Countable.
Yes.
Natural, countable, real, uncountable.
Yeah, right. And but maybe because I'm not really thinking straight, but the way I see is, what's the difference between a real number and a natural number? Except it's the collection of digits, a person, right? You have infinitely long
Right.
decimals, but you could arguably just remove the decimal point and the zero, and that's a natural number.
Yeah, so for the live stream, or for those who didn't hear, the question was about what is really the difference between the natural numbers and the real numbers, and and what you said is the difference. The fact that the real numbers kind of go on indefinitely, like the fact that there's kind of an infinite repetition or like an infinite length behind the decimal point. That is the difference. So the
Natural number not go on?
I mean, the natural numbers are not bounded in size, but there is a limit, so to speak. Like, I'm not sure if I know exactly how to answer the question. Even a rational number, right? Like, if we go back to here, like some of these numbers are a little bit odd or difficult to express in decimals. Like 1/3 is 0.33333 repeating infinitely, but there is still a pattern. Whereas for the large majority of the real numbers or the decimal numbers, like pi, for example, there's not really that same kind of discernible pattern. And so like there's kind of this irreducible complexity of that requires the number to sort of keep going indefinitely, and that's different from the natural numbers.
Yeah, a natural number is of x digits long.
Mm-hmm.
The repeating, as you said, in ties is more.
Right. Cool. I think I saw another hand. So this, yeah. So this is one visual representation of the set of rational numbers, or of positive rational numbers. So from left to right here, we're kind of increasing the denominator, 1, 2, 3, 4, and so on, and as we go down, we're increasing the numerator, 1, 2, 3, 4, and so on. And so this actually has some repetitions, right? Like 1/1 and 2/, like this entire diagonal is actually all the same number. So if you wanted, when you counted, you could take those out and skip them, or you could just leave them in. You're going to end up with the same result either way. You're going to, you'll find the number of rational numbers and the number of natural numbers is the same number. Does that answer the question? Why are they together? You mean, how are these two related? Or, yeah, I mean, this is just a way of representing all of the rational numbers, all the possible ratios between positive integers. And then here, like, it is a slightly different argument. Like, here we're kind of going around these diagonals to show that the number is the same, whereas here we're going down this diagonal to show that the number is different, that there's actually more decimal numbers. And again, like here we started from the very first decimal place to show that there's more real numbers between 0 and 1, but we could have started as far down as we want to show that there's more real numbers between 0.0001 and 0.00001. And yeah, I mean, maybe I'm extrapolating too much and just getting really philosophical for no reason, but like, I don't know, like when you hear some of this religious stuff about like within the tiniest grain of sand contains universes and stuff, I'm like, it's true. I'm like, they showed it. Yeah. Any other questions or comments? Yeah.
Yeah, okay. So I want to preface this with saying I'm not like mathy, so if you're well, I don't know. Yeah, if you can answer the question in a way that is like very, I just don't know math. I get it. Okay. So the question is about the Cantor's infinities picture, the lines, and then the Egyptian like art piece.
Mm-hmm.
So yeah, I guess the question is like, what do these patterns have to do with infinity? Like, how can I see infinity in these patterns?
Yeah, so I guess if we kind of maybe try to draw an analogy with this, like, so if we just take this left part of this line to be like 0 and this right part to be 1, then kind of like the fact that this is kind of filled in, so to speak.
Wait, sorry, left part?
Yeah, let's say that this is 0 and this is 1
Okay,
on some scale.
okay.
Doesn't really matter if that's a foot or an inch or whatever. And so we're saying that we start out with this line segment of total length 1. And then we're saying, let's take away the middle third. And so now we have these two segments that will add up to a length of 2/3. And then we can kind of keep going on in this way. And so as we kind of proceed down this step-by-step process, we're going to end up with a length that's constantly decreasing and approaching 0. But at the same time, because of this argument that we're making, if this argument convinced you, then we're not actually ending up with any fewer points in this whole segment. There's an uncountable infinity between any two points. As long as they're not the same number, we'll always be able to use this argument to say that there's still more real numbers in between.
So could you go back to the other thing?
This one?
Yeah, so basically you're saying like from this big bar on top, there are the same number of points in the big bar as they are like in one of the small bars, like beneath it.
Yeah, and even as these bars keep getting shorter and shorter and shorter, even as the total length keeps getting closer and closer to 0, the number of points doesn't. The number of points remains uncountably infinite.
That seems dumb.
It kind of reminds me of Zeno's paradox, you know? Of like, Zeno's paradox is kind of like this thing. It's like, if I'm walking to this wall and I cut my steps by half each time, I will effectively never get to the wall.
Yeah, and some of these paradoxes are exactly why many philosophers have disallowed this kind of infinity, saying that that you can't have an infinite set, that you can't do this kind of thing, that this doesn't really exist in the world. I think it does. Opinions vary.
I think an analogy that's helping me understand the fractional sort of linear pattern into that image
This one?
is, it's like if 1/1 is just a pi, and then you cut it in half, or you cut it into, in half, that's one thing, and you rebake it, and then it goes back to 1, and then you cut it into 3, and you rebake it, and then it goes back to 8. And over and over and over again. Like, I'm just saying that it's just a little play between separation and integration. Is that like what it's trying to say?
I'm not sure. I mean, to me, this is really just about counting. Like, I don't know. Yeah, I'm not sure if I understood, but if it helps you understand, then that's good.
I kind of say it in my own hopes, maybe it helps other people.
Mhm.
Maybe I don't think it did, but that's okay.
It may have. Yeah, I don't know.
So in the Cantor set, are you saying that, like, is the size of the infinity as the points get closer and closer together, is that staying the same?
It is staying the same.
Okay.
Yeah, and there's different ways to show this. I don't have an image handy, but you can kind of stretch or shrink any interval to kind of map it to another one. Like there's the same, like if you had the entire real number line from negative infinity to positive infinity, there's not any more points there than there are between 0 and 1. And it's really just about stretching or mapping. I'm not sure if that's clear without a picture, but yeah.
If you go back to the diagonal one,
This one or this one?
visualization of the diagonal. Are they both like the same argument? Actually?
They're not the same argument. They're related arguments. But again, this argument is showing that by kind of going around in this way, we can count all the rational numbers 1, 2, 3, 4, 5, and not miss any of them, even though it seems like, I mean, it is like 1, 2, 3, 4 is just this one little piece of this infinite square. Whereas this argument is saying that there's quite a few more real numbers within any interval than there are natural numbers on the entire number line.
Fantastic. I was for the previous slide. What exactly are the operations? Because obviously you were tracing a path earlier,
Mm-hmm.
and is there consistency in the kind of operations, or are you just like maybe our friend here was illustrating like an interplay between integration and division, like, or does this path follow like specific operations?
Yeah, I mean, so this is a set of rational numbers, so really the only operation here is just division.
Okay.
Yeah, these are all ratios, and so the only thing that we're doing with this path is counting.
Cool.
Yeah.
That's actually kind of great in and of itself.
Right. Mm-hmm.
So to go back to the lines, I think what I was trying to say earlier is that it seems like the top line is obviously longer than the line right under it. Like
Mm-hmm.
those segments are shorter.
Mm-hmm.
Therefore, like what I just said, that one's bigger, that one's smaller. So I mean, in some sense, they're all infinite, but like isn't everything infinite?
Yeah, I mean, maybe, yeah. I mean, so you're definitely right that the total sum of the lengths is getting shorter each time. It goes from 1 to 2/3 to, I think this is 4/9, and so forth. But the number of points in any of these intervals is always the same, is always an uncountable infinity.
I guess okay. I guess I'm gonna amend what I said earlier to say that that's cool if you care about points.
That's true, yeah. So, yeah, so a point, again, a lot of people would say points aren't real. Like the idea of a point is that it takes up no space. And some people would say, well, if it doesn't take up space, then it doesn't exist. It's not a thing. And yeah, again, like it all depends on the assumptions that you make. So according to the assumptions that I make, this all makes sense and we have all these weird infinities and stuff. Other people would say that that is not true and that makes no sense at all and has no applicability to the real world. Cool. All right, so maybe some of you are convinced, maybe some of you are not. But what I want to hopefully convince everyone of, even if you don't believe in all this weird infinity stuff, is that there is some structure in everything. And so what I want to do now, again, this is for those in the room, apologies to those on the live stream. What I want to do now is just give everyone in the room a little bit of a chance to just move around and talk to each other a little bit. So as an exercise, I'd like for, and of course you don't have to participate. If you want to just maybe check out the art in the other room or go to the restroom or whatever, you're obviously totally welcome to do what you want. But for those who want to participate, the exercise is to form groups of at least 6 people. Okay, you must have at least 6. You can have, I think exactly 6 is best, but like 7 or 8 or a little bit more than 6 is also fine. Okay, so you can form yourself into a group of at least 6 people. Just introduce yourself to each other a little bit. Tell each other your names. If you'd like to share your gender pronouns. Just something about like why you're here, what is your interest in today's event and topics, just so we can get to know each other a little bit. And then before we come back together, this is the main point of the exercise, try to find a group, a subset of 3 people within your larger group of 6 or more people, where either all 3 of you all knew each other before today, or all 3 of you did not know each other before today. Okay? Form groups of 6, find a subset of 3 where either all 3 of you knew each other already before this event, or none of the 3 each other knew any of the other 2 before the event. Okay, just take about 5 or 8 minutes for that, and then we're going to come back together. Feel free to move the chairs around and that kind of thing.
That's not part of the 6 though, right?
Sorry? It's part of the 6. No, so you can form any group of 6. Any group of just 6 people. Any 6 people, and then this will be the exercise. You can come back to your seat, or any seat is fine. But yeah, but let's go ahead and come all back together. All right. Let's go ahead and continue on with our lesson, sermon, talk, conversation, whatever this is. All right. Cool. So I want to ask those of you who are here in this room. All right, y'all, can I get everyone's attention back to the front of the room? Thank you, thank you. All right. So I just want to ask, was there any group of 6 or more people that was not successful in its exercise? That did not have at least one of these 2 things true? Either 3 people who all knew each other or 3 people who all did not know each other?
Well, arguably, we were talking about this. Arguably, when we formed the group, we didn't know each other. So there were at least people that didn't know each other.
Okay.
And once we shared our names, pronouns, and interests.
Right. Well, I did put before today. I did actually anticipate this. So, all right. So the reason that this worked, this is a mathematical fact called the theorem on friends and strangers. So there's, I think, if I counted correctly, 78 possibilities for how a group of 6 people might know each other or not know each other. But regardless of which configuration it is, one of these 2 things always has to be true. There always has to be, if the group is of size 6 or more, then there always have to be 3 people who all knew each other or all did not know each other. And this is actually, I think, easier to see in this kind of abstract setting of this graph than it actually is to think about in terms of social relationships. If you just think about putting 6 points or nodes together and then connect them all with one of 2 colors, you're not going to be able to avoid forming a triangle of one color. Okay, and if I don't have the materials, like you can also do this exercise with like pegs and string and so forth and try to avoid that, and you won't be able to avoid it. Okay. And so this is just an example of how there's structure in everything. This is a result from a branch of mathematics called Ramsey theory, which I'm going to come back to a little bit later. But it has to do with basically how there's structure in everything. So I just want to talk briefly about the idea of chance and certainty. So again, it doesn't matter how you configure yourself. This was always going to be true because of this kind of deep structure. And there's been a lot of philosophical ideas that people have. Like there's this famous quote from the physicist Albert Einstein that God does not play dice, which I think is still, I think, a common intuition among a lot of people about like the laws of physics, that things need to be deterministic and so forth, which is, I think, contradicted by the current understanding of quantum mechanics, although I'm not some kind of physics expert to really go too deep into that. Yeah, I don't know if God plays dice or not. I think maybe. I don't know. But yeah, this other quote, this is from a paper on another branch of math called random matrix theory, which I think is very interesting. In the very introduction to this whole paper, they talk about the irony to newcomers to this branch of mathematics is that randomness actually imposes more structure and not less. And I think this might be surprising, but it's true. So I just want to just talk briefly about math as I think many of us have experienced it, which I think sadly is not often the best experience that people have in math classrooms, which are often very racist, very sexist, very ableist. And I don't know how many people like read closely the different event descriptions. I didn't put the same event description everywhere, so I'm not sure who read what. But I did mention that I actually used to be a math teacher, and that despite a lot of the harms that I experienced myself in math, I came to love it anyway. But then, unfortunately, I ended up reproducing a lot of those same harms for many of my students, and that's something that I feel a lot of regret for and feel a need to atone for. And it's one of the reasons that I wanted to try to create an event like this, which would hopefully be a more welcoming space for people to experience some mathematics. I think a lot of these issues with math can really start happening from a very young age, where students are often tracked. It's like, oh, you're good at math, you're not good at math when you're in like second or third grade, and then it's kind of like if you're not already set up to go on to calculus and so forth in high school, then you're going to have a very hard time studying math or studying physics or studying some of these other technical fields. And I really think that should not be. The math establishment in general is one of the whitest and malest disciplines out there. And again, I think that there's no fundamental need for this, but I do think that there are political reasons for this. I think it's really because of the power of math, and that some people really have an investment in making sure that power is only held by a small group. Whereas I consider myself to have an investment in just the opposite thing, in seeing like this power and this beauty and this joy to actually be shared among as many people as possible, and especially in my community, among Black folks who are often denied this knowledge. So I want to just take a really quick personal digression and just talk a little bit about my own religious upbringing. So I was raised in a Muslim household, and it was, it's something that has, it's really had a lasting influence on me. So I went to public school in Virginia, where I'm from, and then I also went to Muslim religious school on the weekends. And in a lot of, and I think in both settings, they were very different in many ways, but a lot of them, some of the things were very similar in terms of the obsession with disciplining the bodies of students, making sure that we sit in a certain way, that we don't move around too much, something like that. The focus on rote computation and memorization as opposed to any kind of historical context or social relevance. My education in both settings was very colonial in many ways. I never had a Black teacher of religion or of math. I've never had a Black professor. I'm now a PhD student. I've never had a Black professor in my life. And again, like in the history of math, it's been a very racist history. Like the first African American to receive a PhD in math, that didn't happen until about the 30s. Someone named Albert Frank Cox. And there was another mathematician who was petitioning for him and other Black mathematicians to be allowed to join the Institute for Advanced Study at Princeton, but this was denied. Princeton basically decided, no, we don't want any Black people on our campus, regardless of how knowledgeable, qualified, great at teaching, great at research that they are. There's really just so much to say about this. But I guess I just want to speak a little bit more about the mosque and some of the patriarchal traditions that have really continued to have an influence on me, even as I've started to understand myself, like as a queer person, as a non-binary person, and trying to kind of rid myself of some of the influences of this patriarchal upbringing. And it's something that I really gave a lot of thought to as I was preparing this sermon. So I know for many people, like the word sermon kind of has like a Christian overtone, but again, that wasn't actually my experience growing up. In mosques, there's also a sermon. A lot of times it's referred to by the Arabic name khutbah, but it just means sermon. Like there's a lot of Arabic terms that go untranslated for one reason or another, but it's a sermon. One of the things though, even though I don't consider myself a Muslim or a believer in Islam, it definitely still has a very strong cultural influence on me, including like the belief in like simplicity or in like right practice, as opposed to like right belief in like orthodoxy versus orthopraxis. That could be a whole discussion. And one of the things that I actually really enjoy a lot is this idea of hadith, which are the sayings and doings of the Prophet Muhammad. And there's kind of this idea of like a chain of transmission, which I think has like a really rich applicability to math as well in metaphor. And there's, I think, some really great sayings. There's one that's like, leave alone that which involves you in doubt and adhere to that which is free from doubt, for truth is comforting. And I was like, damn, like, all right. That's what I really find in math. Like, I really find like some of the structures that we were exploring, whether with infinity or just a simple theorem on friends and strangers, to be comforting. But I realized that even in spaces like this, where we're really making an effort to be welcoming to people from all kinds of different backgrounds, there's still so much that we do have to worry about. Like, so I'm also a political organizer for police and prison abolition. And infiltration by police is often one of the main things that we have to spend a lot of time worrying about. And that's something that I was really exposed to from a young age. So I was born in 1989. I'm 30 now. So 9/11 happened when I was 12, and there was quite, an enormous racist backlash against members of my community after that. And even from a young age, like as a teenager, I would hear jokes about how like informants were actually the ones who were keeping the mosque in business. Like it wasn't actually people who were going to like pray because of belief, but like it was the FBI sending people. But like they also had to like donate money to like shit. So, yeah. And I didn't want to open with this, but I did want to share just this really brief clip that I think about a lot, like especially when I'm speaking in. I think this is a more intimate setting. Hopefully, hopefully not this issue, but here's a little clip from one of Malcolm X's most famous speeches, "The Ballot or the Bullet." This is his introduction, his welcome.
Mr. Moderator,
If I can play it.
Reverend Clee, brothers and sisters, Mr. Moderator, and I see some enemies. Clee. Mr. Moderator, Reverend Clee, brothers and sisters, and friends, and I see some enemies. In fact, I think we'd be fooling ourselves if we had an audience this large and didn't realize that there were some enemies present.
So I think it's really unfortunate that when building community, whether around math or around politics or whatever it is, that we have to kind of maintain this consciousness about informants, about people who are here for some other reason than the actual purpose of the event. But for all that, I again, even though I don't consider myself religious in a traditional sense, I have this weird math religion instead of any traditional religion. Again, I do draw a lot of comfort and inspiration from the resilience of Muslim communities specifically in continuing to build community and to gather together, even knowing in the face that there are these informants and provocateurs, and that the state is sending people into these communities. I mean, really, in many cases, deliberately targeting the most vulnerable members of the communities to recruit them and say, like, hey, we're going to give you some money if you carry out this terrorist plot or whatever nonsense. Someone who had no conception or idea of ever doing this in their life until the state realized, like, oh, this person is desperately poor, and if we manipulate them in this way, then we'll be able to basically, like, win a conviction. And it's really unfortunate that this is the state of many religious communities and political communities today. And I think for me as a police and prison abolitionist, I also draw comfort, again, from this specific tradition involved in my upbringing, but also from other traditions. So I'm not a Christian, but I do draw a lot of inspiration from a very Christian speech given by Frederick Douglass, which I read at least once every year, called "What to the Slave is Your 4th of July." And I really, before, we're going to take a little break in just a moment, but before we get to that, I just want to take a moment to just read some of the power of his words. So in a lot of ways, it's, again, very specifically Christian, which is not my own tradition, masculinist, maybe, problematic in any number of ways, but I'm going to read some excerpts just as they're written. And I hope that maybe some others can also draw some inspiration and comfort from these words. So it's a long speech. I really recommend reading the entire thing sometime if you have the time. I'm just going to read a few excerpts now. He kind of starts, let me not give the whole overview of the entire speech. But he basically is talking about, so this speech was given in 1852, before the Civil War, before my ancestors freed themselves by arming themselves and fighting against slaveholders. And he talks about, he really goes in on America as a whole, and specifically on the Christian church from a Christian perspective. He talks about how whether we turn to the declarations of the past or to the professions of the present, the conduct of the nation seems equally hideous and revolting. America is false to the past, false to the present, and solemnly binds herself to be false to the future. Standing with God and the crushed and bleeding slave on this occasion, I will, in the name of humanity which is outraged, in the name of liberty which is fettered, in the name of the Constitution and the Bible, which are disregarded and trampled upon, dare to call into question and denounce, with all the emphasis I can command, everything that serves to perpetuate slavery, the great sin and shame of America. I will not equivocate. I will not excuse. I will use the severest language I can command, and yet not one word shall escape me that any man whose judgment is not blinded by prejudice or who is not at heart a slaveholder shall not confess to be right and just. All right, so he's really going in. He's going hard. In 1852, this black man is speaking to like this predominantly white audience in Rochester, New York, and he's not afraid to say exactly what he thinks, and he anticipates a lot of these objections right away. I fancy I hear somewhat of my audience say, it is just in this circumstance that you and your brother abolitionists fail to make a favorable impression on the public mind. Would you argue more and denounce less? Would you persuade more and rebuke less? Your cause would be much more likely to succeed. But I submit, where all is plain, there is nothing to be argued. What point in the anti-slavery creed would you have me argue? On what branch of the subject do the people of this country need light? Must I undertake to prove that the slave is a man? That point is conceded already. Nobody doubts it. The slaveholders themselves acknowledge it in the enactment of laws for their government. They acknowledge it when they punish disobedience on the part of the slave. He goes on for a while. When the dogs in your streets, when the fowls of the air, when the cattle on your hills, when the fish of the sea and the reptiles that crawl shall be unable to distinguish the slave from a brute, then I will argue with you that the slave is a man. For the present, it is enough to affirm the equal manhood of the Negro race. And that's how I feel about so many things, right? Like, I don't need to argue, I just affirm. Like, I'm trying to give some of these arguments about math and so forth, but again, like, I don't claim that it's really a logical argument. For me, it's enough to affirm. He goes on talking about, he basically asks, how should I look dividing and subdividing a discourse to show that men have a natural right to freedom, speaking of it relatively and positively, negatively and affirmatively? To do so would be to make myself ridiculous and to offer an insult to your understanding. There is not a man beneath the canopy of heaven that does not know that slavery is wrong for him. Am I to argue that it is wrong to make men brutes, to rob them of their liberty, to work them without wages, to keep them ignorant of their relations to their fellow men, to beat them with sticks, to flay their flesh with the lash, to load their limbs with irons, to hunt them with dogs, to sell them at auction, to sunder their families? He goes on, must I argue that such a system stained with pollution is wrong? No, I will not. I have better employments for my time and strength than such arguments will imply. What then remains to be argued? Is it that slavery is not divine, that God did not establish it, that our doctors of divinity are mistaken? There is blasphemy in the thought. That which is inhuman cannot be divine. Who can reason on such a proposition? They that can may. I cannot. The time for such argument is past. He goes on. The next section is the most famous, where he talks about how the celebration of the 4th of July is really a sham and a mockery. Again, I really recommend the entire speech, but I want to skip ahead to the part where he specifically addresses the church. And I think, unfortunately, many of his words are just as applicable today as they were in 1852. He's speaking specifically in the context of the Fugitive Slave Law of 1850, which essentially required all U.S. citizens to participate in slave hunting. There was a great amount of resistance to this law, including from Northerners who didn't necessarily, wouldn't necessarily be considered anti-racist by today's standards, but they were still very much against this. And he speaks about how he takes this law to be one of the grossest infringements of Christian liberty, and if the churches and ministers of our country were not stupidly blind or most wickedly indifferent, they too would so regard it. At the very moment that they are thanking God for the enjoyment of civil and religious liberty and for the right to worship God according to the dictates of their own consciences, they are utterly silent in respect to a law which robs religion of its chief significance and makes it utterly worthless to a world lying in wickedness. He talks about how essentially they're really concerned with ceremony, but not really concerned with humans, with actually doing anything to make the world a better place. The fact that the church of our country does not esteem the Fugitive Slave Law as a declaration of war against religious liberty implies that the church regards religion simply as a form of worship, an empty ceremony, and not a vital principle, requiring active benevolence, justice, love, and goodwill towards man. It esteems sacrifice above mercy, psalm singing above right doing, solemn meetings above practical righteousness, A worship that can be conducted by persons who refuse to give shelter to the houseless, to give bread to the hungry, clothing to the naked, and who enjoin obedience to a law forbidding these acts of mercy is a curse, not a blessing to mankind. He talks about how the church of this country is not only indifferent to the wrongs of the slave, it actually takes sides with the oppressors. From this Christian perspective, Frederick Douglass says, I would say welcome infidelity, welcome atheism, welcome anything in preference to the gospel as preached by these divines. They convert the very name of religion into an engine of tyranny and barbarous cruelty. These ministers make religion a cold and flinty-hearted thing, having neither principles of right action nor bowels of compassion. They strip the love of God of its beauty and leave the throng of religion a huge, horrible, repulsive form. It is a religion for oppressors, tyrants, man-stealers, and thugs. A religion which favors the rich against the poor, which exalts the proud above the humble, which divides mankind into two classes, tyrants and slaves, which says to the man in chains, stay there, and to the oppressor, oppress on. It is a religion which may be professed and enjoyed by all the robbers and enslavers of mankind. All this we affirm to be true of the popular church and the popular worship of our land and nation. A religion, a church, and a worship which, on the authority of inspired wisdom, we pronounce to be an abomination in the sight of God. He quotes the book of Isaiah, saying, bring me no more vain oblations. Incense is an abomination to me. The new moons and Sabbaths, the calling of assemblies, I cannot away with. It is iniquity, even the solemn meeting. Your new moons and your appointed feasts my soul hates. They are a trouble to me. I am weary to bear them. And when you spread your hands forth, I will hide my eyes from you. When you make many prayers, I will not hear. Your hands are full of blood. Cease to do evil, learn to do well. And I think it's very unfortunate that I really feel the need to address so many of the popular religions of this land really in the same way today. So I've been a member of a campaign called No New Jails, and there are many religious leaders who have essentially been endorsing the construction of new cages for human beings, as if their own religion did not tell them, to visit those in prison, to free those who are in prison. It's remarkable. And Frederick Douglass goes on. I'm gonna close here. He says, in prosecuting the anti-slavery enterprise, which I consider the abolitionist enterprise today to be a continuation of the same thing. In prosecuting the anti-slavery enterprise, we have been asked to spare the church, to spare the ministry. But how, we ask, could such a thing be done? We are met on the threshold of our efforts for the redemption of the slave by the church and ministry of the battle, by the church and ministry of the country in battle arrayed against us. We are compelled to fight or flee. From what quarter, I beg to know, has proceeded a fire so deadly upon our ranks during the last 2 years as from the northern pulpit? As the champions of oppressors, the chosen men of American theology have appeared, men honored for their so-called piety and their real learning. And he goes on to call a number of them out individually by their names. I wanted to do the same thing today. Unfortunately, I didn't have enough time to research this week, but maybe I can go ahead and add that back later. He goes on after naming them, saying, condemning how they taught us against the example of the apostles that we ought to obey man's law before the law of God. He says, my spirit wearies of such blasphemy. And I truly feel the same way today. So with this, I'd like for us to just go ahead and take a short break. We're going to come back, get back to a little bit more discussion of math in about 10 minutes. But again, just for those who haven't been in the space before or who are not here at the beginning, if you need to use the restrooms, they're out through the doors to your left. There's also a few art pieces that some artists have kindly brought here for us on mathematical and spiritual themes that you can check out in the back room. And then in about 10 minutes, we'll go ahead and come back together. Of our sermon. Again, thank you all so much for your presence today. It's a great picture of John Coltrane, right? I really like this illustration. All right. So what I would like to do now, we're already running a little bit late. I don't want to keep you all too long. but the food is also running a little bit late, so I'll keep you just a little bit late too. Yeah, I do want to just reprise. I think I see a lot of different faces from last year. Actually, I think there's only a few people who were at the last iteration of this event. Last year, like I mentioned before, I did not give a sermon, but more of like a history lesson. I just want to reprise a few of those elements. So math, of course, is old, very old. So over here on the right, we have a picture of kind of a clay tablet from ancient Sumer. And a lot of the math that they actually used in those days still has its influence today. So they actually, rather than the base 10 that we're most familiar with, they actually counted in base 60. And that's actually where like minutes and hours and seconds and things like that come from, and degrees. They would represent fractions in different ways, and they kind of had a place value notation that made arithmetic, and especially multiplication, a lot easier than like Roman numerals and some of these later representations. They're really interested in geometry and division problems. That's actually what this clay tablet here is a representation of. And they assigned geometry homework, much like the homework that I assigned when I was a high school math teacher myself. Most of my understanding, I'm not an archaeologist, but my understanding is that most of what is preserved was preserved by accident. Like if, so they would actually reuse the same clay tablets over and over again. But if there was a fire, then it would get baked in. And so what is preserved is just whatever was the homework at the time when the school caught on fire. So in Egypt, there was also a really rich tradition of mathematics dating back, I think, about 5,000 years or more, at least from 3000 BC. So this here on the right is an image of what's called the Rhind Papyrus, which is currently held by colonizers in the British Museum. And there's actually a few fragments held by colonizers in Brooklyn as well, at the Brooklyn Museum. And this is like a huge topic of controversy, especially in Egypt, where people, I think, rightly believe that their cultural heritage should be there and able to be accessed by Egyptians, rather than being held, very far away. But yeah, I guess in many of these traditions, in many of these ancient mathematical traditions, the link between math and religion was very close. Even being able to count was considered a very arcane and sacred art. And the introduction to the Rhind Papyrus can be translated as accurate reckoning, the entrance into knowledge of all existing things, and all obscure secrets. And I'm just like, wow, I really want that. So yeah, I guess I want to just talk a little bit about model and metaphor, language, representation, and translation, and kind of what I've often experienced as sort of this claimed opposition between literary and quantitative knowledge, or like art versus science, which I think is really just not accurate. I believe in a governing unity. And I want to just play a little bit with these two quotations, which really they're using the same word disorder really in two totally different contexts. Like they're really not actually talking about the same thing. But I still think it's very interesting to try to put these two things in conversation. So Frantz Fanon was a very important black revolutionary, originally from the French colony of Martinique, who fought in the Algerian War of Independence against France. He wrote a famous book called The Wretched of the Earth, and in it, among other things, he said, "Decolonization is a program of complete disorder." Now, earlier when we were talking about the theorem on friends and strangers, I mentioned briefly that this comes from a branch of mathematics called Ramsey theory, which can be understood as asking essentially how many elements of a structure are necessary before some type of order emerges necessarily. And one of the kind of catchy ways that this branch of math has been summarized by this mathematician named Theodore Motzkin is complete disorder is impossible. And so this is kind of this tension that had in my mind for, I guess, some years now that I just wanted to share and maybe try to provoke some other thoughts. And if you have thoughts, then you can share those with me too. About some of the issues that we face when trying to decolonize. I mean, first of all, the land, right? That decolonization is not a metaphor. That, the land that we're on right now is unceded Lenape territory. And Lenape people are still struggling, including having a prayer camp called Split Rock, where they were attempting to prevent a pipeline in New Jersey, what's now called New Jersey, the Ramapo Lenape, very, very nearby to here. And, I do think that this kind of literal, physical, geographical decolonization is the task in terms of just the political spaces and the social spaces that we're in. But I do also think that it has to do with other branches of knowledge like mathematics. So another quotation from Frantz Fanon, he spoke about how Europe is literally the creation of the colonized peoples, that the wealth which smothers Europe is that which was stolen from the third world or the global south or whichever name you want to give to it. And I really would apply that to a lot of mathematical knowledge as well. Like I was giving the example earlier of how George Cantor drew inspiration from Egyptian art, which one of his family members was a researcher in. And in general, a lot of mathematical theories and knowledge were also developed in colonial contexts in terms of quantifying people and kind of oversimplifying a complex reality. At the same time, I want to resist the idea that there's something inherently colonial or wrong with quantification or with math, because I truly believe that it has a liberatory potential, that it is a very powerful tool which can be used for all kinds of purposes other than the ones that unfortunately the powers that be have largely chosen to use it. So I want to talk a little bit about projection, reduction, abstraction, summarization. These terms are not quite synonymous, but they're pretty close. And earlier in the same speech that I was quoting from before by Frederick Douglass, he's kind of setting the scene. Frederick Douglass is speaking about what I would call the U.S. settler war of independence, what some others would call the American Revolution. And yeah, it's quite remarkable, right? Because, of course, he's speaking in his own time. He's kind of thinking of himself as like a modern person versus that era, which was not long ago, still within living memory. But at that time, as he puts it, neither steam nor lightning had been reduced to order and discipline, right? Like in Frederick Douglass's time, in the 1850s, there were steamboats and all kinds of technologies that did not exist. People were able to travel much faster up and down even the eastern seaboard of the 13 colonies than had been the case in like the 1770s or 1780s, where it would take days to get from Delaware to Virginia. And I really just think this idea of reduction is so interesting. So obviously what I have here is kind of this flat 2D screen, but you can kind of imagine, or hopefully this image helps you see some of kind of this idea of 3 dimensions, right? An x-axis and a y-axis are what we're often most familiar with when looking at a flat surface, but there's also like a z-axis coming in and out. And there are different ways that we can flatten or reduce or abstract or project or summarize this kind of complex 3-dimensional image into something simpler, right? So if we have a 3D volumetric shape like a cylinder, if you project it one way, you'll get a circle. If you project it another way, you'll get a line. And that's kind of a reduction. And there's a sense that I'm not going to really get into, but there's actually a precise mathematical sense where you can actually multiply shapes, and you can multiply a circle times a line, and you get a cylinder. It's kind of the converse or the reverse of this process. And I really just find these models and these metaphors to be so rich and fascinating as I think about some of the larger political struggles that I'm engaged in. So it becomes more difficult to visualize when you have more than 3 dimensions, right? Because we can only see that many. But even in physics, right, there's a notion of a 4th dimension of time and space-time, which I'm going to return to at the end of this talk. Or in general, I've been trying to develop this metaphor for a few years, but I haven't actually had the time to really sit and do the programming or the coding to think about it. But I guess I've been kind of thinking about different dimensions of struggle or identity or experience. I've been kind of trying to imagine this map where maybe we could represent different elements of a person's positionality, whether that's in terms of race or gender or sexuality or ability or nationality, right? Like there's income, wealth, there's not really a limit to how many dimensions that we could collect about a person if the data was available, whether from some kind of census tract or from voluntary submission of data. And there's some really interesting techniques for dimensionality reduction. There's two in particular that I'm interested in learning more about, and I'm really curious. I know there's a lot of knowledge in this room and in this community, and if folks want to share with me at some point, I know that there's two in particular. One is called T-SNE, T stochastic neighbor embedding, and another called PCA, principal component analysis, where the idea is essentially to reduce the dimensions without losing too much information, to kind of try to keep as much of the information as possible. And so you might start out with like a very high dimensional space, and then you can reduce it or project it onto just 2 or 3 dimensions in order to be able to visualize it without losing too much of the information that was originally there. You have to lose something because you have fewer dimensions that you ended up with than you began. But in many cases, you really don't have to lose much at all. You only lose a little bit. And I've been really trying to just kind of think about some of these metaphors and how they might be helpful in visualizing some of our imaginaries of the future, for thinking about how our positionalities might change, thinking about these things not as being static over time, but actually as changing over time. And again, I really believe that mathematics has so much to offer in terms of these kinds of metaphors. To me, there's really no difference between a mathematical model and a metaphor. They're just two representations or abstractions of the same thing. So the idea of multiple representation, I think, is really interesting across language, literature, linguistics, as well as math. I want to just take a moment to talk about binary representation, which I think may be familiar to some of you, but I will not assume it's familiar to everyone. So typically when, I think most of us, maybe probably all of us, are most used to counting using the decimal system, right, where we have digits from 0 through 9. And then when we run out, so to speak, of digits, we increase the place value, right? So we would count from 0 up through 9, and they go to 10. We have this 1, 0. Binary, the idea is really the same. It's just that you have fewer digits before you run out. You just have 0 and 1. So you would start counting from 0, and then you would go on to 1, and then 1, 0 would translate to 2 in a decimal representation, and so forth. So this is typically the representation that's used by computers. And I think many of us are in the habit of thinking of binary representation as something that is very much modern and really based in computers, but actually it has much older roots in Africa, in West Africa specifically. So I'm not able to speak that much about this. Actually, my co-organizer, Zay, would be a much better person to ask about this than me. But I do know that in the IFA divination system, that as far as I know, according to my limited research, this is actually the oldest binary representation that exists. Actually comes from IFA divination, and eventually traveled to Europe, became kind of recast as geomancy, one of these other kind of divination systems, and then from there eventually made its way to become the primary representation in computers. And yeah, again, like going back to the Frantz Fanon quote about much of what we think of as Western or European culture as actually being the creation of us as colonized peoples, in this case specifically Black people. I think it's really important for us to keep that in mind when we think about how we relate to these larger systems of math, of computing, and of these other things. It's not something that it may seem foreign to us because of the ways that English bias has taken over the ASCII character set and so forth, but it's actually not something that's intrinsic to math, to computation, to representation. So I just want to talk for a quick minute about just divination in general. Yeah, if you look up like list of divination methods or something like that on Wikipedia, it's a really long list. I'm like, wow, people really tell the future doing anything. Which I've actually like at first I thought was really weird, but I've actually started kind of getting into it recently. Like I was reading, let's see, there's one called tasseomancy, which is reading tea leaves. There's claromancy, which is reading by lots, like reading by chance. Eruspicina is reading the future by reading animal entrails. Astrology, of course, is trying to tell the future by reading celestial bodies. Let's see, there's one called transatomancy, which is telling the future by things that you accidentally saw or accidentally heard. Numerology, reading numbers. And it's really interesting to think over history of like how what is considered science versus pseudoscience changes over time, like how historically flexible these categories are. I really, in a lot of ways, I'm not sure how much difference there really is between, trying to tell the future based on the stock market or some of these economic predictive methods compared to some of these older methods. I'm really not sure that there's any specific difference. But yeah, I guess just some of these quantitative measurements can seem really strange. But I think it was in the Talmud. There's a quotation that dreams are 1/60th of property, and sleep is 1/60th of death. And I just love that quantity, like 1/60th. Like it's such a specific quantity. Like I think again it goes back to Sumer, to minutes, seconds, and so forth on the clock. 1/60th. It's small but significant, right? It's perceptible. It's only a small fraction of the whole, but it definitely matters. I don't know. Sorry, let me just pause for a minute. I don't know if anyone just has anything that they want to share about divination before I move on to the next topic. 60 dreams would add up to a prophecy, or?
I like that you heard prophecy, but
Oh.
wouldn't be property though. Some of all parts, not equally.
Yeah. I'm not sure that you can necessarily add it up in that way. I don't think so. So far, I'm still. I don't know if y'all seen that meme that's going around where it's like a little of something as a treat. It's like, where it's like God's like let him have a little death as a treat, like as sleep. Cool. So I want to just revisit Cantor's diagonal argument for just a moment using binary representation. Pardon me. So this is the same argument that we saw before. You see that there's not really a decimal point now, but the idea is the same. It's just that now we're dealing with a binary representation rather than a decimal representation. And I guess one of the things that I kind of like about this, maybe it shows that I also don't like dice or something, I don't know. I guess one of the things that I like about the same argument in a binary representation is that there's no arbitrary choice anymore. Now it's like if you don't want a 0, you've got to have a 1. If you don't want to have a 1, you've got to have a 0. And I just think that this makes the diagonal argument like a little bit more cute. I don't know if people agree with my sense of like what is cute in like a math argument. But yeah, I guess there's something really, I think a common sense of taste, like because I think many mathematicians do think of mathematics as like being an art, as being a creative endeavor. I think simplicity or minimalism is often considered appealing, and I think I share that. And so again, I just want to just take another moment to just linger on this diagonal argument about how to create a new binary string, which is not on this other list of binary strings. According to the same diagonal argument, but without that element of arbitrary choice. I'm not sure if I got this taste from math class or traditionally in Muslim religion, gambling is forbidden. So, like, again, I know that cultural influence is something that has stayed with me very much. But yeah, I guess I also often like going back to the theme of divination for a moment. I feel like gambling is really hard to avoid. You know. Like I got my lease renewal And it was like, all right, if you renew your lease for 1 year, you pay this much, and if you renew it for 2 years, you pay more, but you lock it in. And I'm like, well, I don't know what the rent guidelines board is going to vote next year, so I kind of feel like I can't actually avoid gambling, like just to not move, you know. And I guess it's just another example of just math governing things. I mean, yeah, I'm sure not everyone thinks of it that way, but I do. So one of the things with these infinities, so there's a notion which I haven't got into a little bit, which I didn't really get into before, but I want to get into now, about fractals. So fractals, for those who aren't familiar, are self-similar structures where you kind of zoom in, so to speak, and you kind of keep seeing the same pattern again. And many people would say that they don't strictly exist in nature, or I think most physicists, biologists would say that they don't strictly exist, but it works up to a certain approximation, so to speak. Like this is a particular type of fern, which I did not put the note. I forget what kind of fern this is called again. But you can kind of, you may be able to see that we have kind of this whole fern with all these leaves, and if you zoom in on any particular leaf, there's just kind of more of the same pattern over and over again. There's actually quite a few plants that have this structure. During wintertime, you can actually see this on a lot of trees with their branches. Romanesco broccoli has this structure. And it's not something that's only limited to plants. Like lightning also kind of has this kind of fractal branching. And again, for me, I'm not a physicist or a biologist. I think of myself more as an organizer and as an activist. I guess more as an organizer than an activist, but let's not get into the difference. I think I'm really interested in the way that these fractals can actually be applied to social questions and social issues. So we live in a very starkly unequal world, largely divided between the globe, like kind of at the largest scale, zoomed out the most between the global north and the global south, where there's a few countries, mainly in the U.S. and Europe, which have only a minority of the world's population, but control a large majority of the world's income and wealth. And that's a really stark and striking and racialized division that is very problematic and bad. And I think reparations are due to the large majority, or really all colonized peoples around the world. However, I think it's also really interesting that you can actually see similar patterns at smaller geographical scales as well. That, like within the U.S., for example, you have a few concentrations of wealth in places like the Bay Area in California or New York, where we are, versus a lot of more impoverished territories in the middle. But then even within a place, even within a city like New York, maybe NYU, where I go to school, the people who are living in that neighborhood have this very high six-figure income. And then very nearby on the Lower East Side or a train ride away in the Bronx, you have some of the poorest communities in the country. And I'm actually really interested in trying to use this fractal metaphor to even go a step deeper, to think about the ways that gendered inequality is actually similar to these kind of global north, global south inequality. Or even to take it a step deeper and actually go into the mind of a colonized person and actually try to think of the ways that we reproduce some of these harms and some of these structures even in our own minds and in our own actions. I think, again, this kind of mathematical knowledge, theorizing metaphor could be of enormous value to our communities if we're able to bring that kind of mathematical knowledge and develop it. Although, unfortunately, I don't think that NYU is really the kind of institution that is going to be bringing that kind of mathematical knowledge to more people. So this one is more just one for being pretty. I'm just going to play this. So this is a famous fractal called the Mandelbrot set. I'm just going to play this little video. So again, we see this kind of self-similar pattern, where as we zoom in, you kind of keep seeing the same pattern. There's some really interesting ones in here. Check it out. Yeah, I'd like to try to describe this for accessibility, but I really have no idea how to describe this visual with words, unfortunately.
I can describe it. It's like a trippy. Yeah, it's like a trippy thingy, and it's like swirling around, lots of colors. Like if you focus on like one thing, you go like because it like becomes other thingies. It kind of looks like galaxies. I don't know if that's like helpful, but like yeah, it's very cool. And again, trippy is the word.
Thank you. Would anyone like to add to that description? Well, let this go for another moment.
Seems like
It's for the live stream, for accessibility, if you could use the mic.
sure. It just kind of seems like you'll never reach the end.
Yeah, that's accurate. There's no limit to how far you could zoom in theory. In practice, to produce a visualization like this, you have to use a certain amount of computational power. The farther in you want to go, the longer you're going to have to run your code and so forth. But there's no theoretical limit as far as I'm aware. I think it's only a practical computational limit. Okay.
It seems like to not go is like to, like I would imagine that it goes into the center into a point, but it doesn't feel like that visually. Like it kind of, does that make sense? Like you see how the light is sort of moving, like that center field is like going over to the left, and now I see it all in different places, and now it's not, there's no locus point.
I literally feel high.
Yeah, yeah. So I think the person who produced this visualization is basically choosing manually, like where do they want to zoom in, because there's so many different complex structures that are embedded within this one mathematical set, and I think that they just kind of made some arbitrary decisions about which ones they thought would be interesting to show to people.
The locus is simultaneously everywhere.
Right, it's bugging me out, but yeah.
Can you define a fractal again?
Yeah, I can try. A fractal is a mathematical structure which is self-similar. So it's kind of recursive. It's defined in terms of itself. So as you keep zooming further in, so to speak, or in this case in, you could also, I think, do it out. But as you keep, it's a little bit actually similar to the Cantor set that we saw earlier, in that you kind of keep repeating the same iterative process in order to create a structure that has unlimited depth or complexity. Is that helpful? Somewhat? A little bit?
Yeah, it's not what I thought it was gonna be. I thought like when you zoom in, you're gonna keep getting the same image.
Mm-hmm.
But this is changing a lot. Like I've noticed maybe there's like a loop. Like some of the images I'm recognizing, but then it feels like we're also seeing different things. But then it just feels like you're just zooming in.
Yeah, I think there's different fractals that have different structures. Like I think there are some, and I think even with this one, depending on where you zoom in, like you would kind of see the original image more and more. But if you choose a certain point, then like all this complexity was there in the original image. It's just that the resolution wasn't such that we could have actually seen it.
Right, but then that just feels like you're zooming into the image.
Mm.
Because it doesn't have the exact same pattern.
Mm-hmm.
Like this I see as, okay, we're seeing the infinity in the image that existed in the image. But yeah, I'm having a hard time relating that to a fractal.
Mm-hmm. Yeah, I mean I think the other examples of like the fern and the lightning are like kind of simpler examples than this one. Yeah, I see.
The mathematical definition of a fractal is based off of self-similarity, but in practical applications, it's not based off of self-similarity. So Benoit Malebranche, the guy who actually created fractals, theorized that like there's not really a way to define them in the real world, but the closest approximation is using the box counting dimension, which is essentially that if you take the side of something, so if you take the side of a cube and you double the side of that, you double the length of that, and then you increase the volume proportionally, how much does it scale by exponentially? So a cube scales exactly by 3
Yeah, there's a notion. One of the things I think one of the reasons fractals are called fractals is because there's this notion of a fractional dimension. Like I think typically we're used to thinking of dimensions in integer terms, where it's like it's a line or it's a square. It's either dimension 1 or dimension 2. But some of these shapes, like yeah, actually, it might have been helpful if I had included an image of the I don't know if it's pronounced cock or coke, Koch snowflake. That might be one that's interesting to look up later for those who are interested in these topics. Where yeah, it has a dimension between 1 and 2. It's kind of somewhere between like a line and a 2D shape. Yeah, fractals are cool. I'm just gonna go ahead and move on. I'm gonna skip about fictional religions. Maybe I'll come back at the end if the food is still late. But I want to move. So yeah, again, I just kind of want to zoom out to this sense of wonder that I really get from mathematics. That I hope maybe folks who haven't felt that before might feel a little bit of now. Maybe I convince you a little bit. So there's this quote from Gauss, a mathematician from I forget 17 or 1800s, that mathematics is the queen of the sciences and number theory is the queen of mathematics, which is kind of a weird quote. It's like, how did math get gender and like number like, it's kind of strange. But yeah, so number theory is a branch of math. It's a branch of pure math. Like there's branches of math like geometry, which very much, even though they've now become very abstract, they still very much betray their historical origins as applied. Like geometry literally means measuring the earth, like if you look at the etymology, because that was the main application that people had for geometry back in the day. Now it turns out mathematicians will tell you geometry is actually not about measuring the earth. That like measuring the earth is one thing you can do with geometry, but there's a million other things that you can also do with geometry. And number theory is based on number theory, based on the properties of primes, specifically the difficulty of factoring prime numbers, or at least what's believed to be the difficulty of factoring prime numbers. It hasn't been proven, but no one's found a way to do it quickly, or at least if they did find it, they didn't publish it. They didn't tell anyone. Although there have been cases where the NSA discovered things and then didn't tell anyone, and then someone else had to rediscover it later. So that could be, but I don't think so. I think prime numbers are hard to factor. I can't prove it. And yeah, I think, I mean, maybe this will be proven wrong. This has to do with an important problem in mathematics and the theory of computation about two complexity classes, P and NP. You could look that up later if you're into that. Like most people, my intuition is that these two complexity classes are not the same. Kind of intuitively, I'm going to speak very roughly. You can think of NP as finding a problem to certain computational like complexity problems, and P is checking the answer. And there's kind of this intuition that finding the answer in the first place is harder than checking it. I'm speaking very roughly, very imprecisely, but that's the rough idea. And so, like most people, I have kind of this intuition that they're not the same, but it hasn't been proven. And I find it really remarkable that the universe would allow someone like me with really insignificant resources to use kind of this property to protect my communications from an entity like the NSA, which has immense resources at its disposal. I think that must mean something. It must be something really deep. But even though I have this belief in math, I definitely don't have the same faith in the computers which are used to realize this math in practice. I mean, there are so many ways that these machines can be infected and taken over, different what are called side channel attacks in cryptography to kind of use timing and other weird things in order to get out information that you shouldn't be able to in theory. And yeah, I mentioned that I'm a PhD student now. I'm a novice researcher into the materiality of computing, the ecology of computing, like where these metals come from, who puts them together, how are those people treated? Not very well. You may already know. And yeah, I don't know. It's something that I'm really trying to hold these two things all at once, like both the beauty and the wonder of math and kind of the ugliness of how it's realized and used in practice. I really would like to harmonize these things and for us to see a different use, for us to see something different in math. So I want to start to close out with some notes about time. Speaking of climate change and some of these things. So this is a metaphor of, like, suppose that this is just the time of representing basically the time from the formation of the earth and the origin of life until now, as like the length of an arm. So there's all these weird names: Proterozoic Eon and Phanerozoic Eon and a bunch of stuff I don't really know about. I don't know how to pronounce. But basically, life has existed since all the way back here. And then humans have really only existed for like the tip of a fingernail. Like if life has existed for as long as my forearm, and then I took a nail file and went like this, then humans would disappear. So humans are pretty recent in this whole thing, right? But what we see now with catastrophic climate change is the way that certain humans, and I think it's really problematic how people will be like, humans, humanity, broadly. It's like, which humans, you know? It really has a lot to do with white supremacy and colonization and imperialism, you know, in terms of which humans are actually digging up all of these, digging up the oil and the coal and so forth, basically in order to be in such a big hurry. Like some of these fossil fuels are the better part of 1 billion years old, 650 million years old or more. And then in a span of 200 years, like a completely insignificant time span on a geological time scale, certain humans have dug up an enormous amount of it and burned it, kind of released all that energy in the atmosphere with the consequences that we're starting to see today, when with very uneven impacts across different groups of people. It's really largely racialized and colonized peoples in the global south who are facing the worst consequences of this. And I don't know, it's one of these things, again, like just thinking of math and time, like the way that this really short span could have so much influence on the larger earth, the larger ecosystem, on all of us. Yeah, I want to speak a little bit just more about time and the idea. I want to relate this to the earlier discussion about dimensions and dimensionality. So I was speaking, I mentioned briefly earlier that according to the current understanding of physics, space and time are inseparable, right? And so, yeah, I have so much to say about that, like in terms of just like how knowledge is organized and divided, right? Like they have this field called history and they have this field called geography, and I'm like, how are you separating these? This makes no sense. Like I have so many issues with the way that I've been taught in the past. Really, in fact, space and time are inseparable. And so there's this notion of like a world line. And so like suppose that you had a point and you kind of see how it travels through time, and then there's a notion of like kind of how people come together, kind of like the way that maybe we're coming together in this room. Like our world lines are kind of colliding, like when we have conversations or when we speak about these things. But the notion of a world line is really maybe not quite accurate, because that would like be like a point traveling, right? And kind of like we were discussing earlier, like in theory, a mathematical point takes up no space. In fact, we take up space. We have a volume. And so it would actually be more accurate for us to speak of like a world volume or like a world tube. And so it gets a little bit more messy this way, right? But it actually kind of allows for the possibility of collisions and overlaps and these other things in a way that kind of the strict notion of a world line doesn't. And yeah, I guess I just want to, before I close out, I want to just thank all of you for colliding your world lines or world tubes with mine. I really appreciated the comments that folks have shared, the knowledge that you've generously shared with me and with each other. I know the food is still running a little bit late, so I don't want to close quite yet. But actually, I did plan for one more thing. You'll see it in the slides in a moment anyway. But yeah, I really just wanted to thank you all. And before I say my own closing remarks, I just wanted to open up the space if anyone wants to come up here and just say any affirmations. Like if you just want to say anything about your own beliefs, about what you gained from this day, I invite you to come up. If you'd like, you can come up and take the stage. I would ask, I mean, you don't have to if you don't want to be part of the recording, because this is being live streamed and recorded. But ideally, if you would like to do that, it'd be great if you would come up here and use the mic for accessibility for those who are not here with us in the space.
I actually just had a comment and a question. I'm not sure if it's
If you want to come up, I think that's.
Sweet. I don't know how to use one of these, but cool. Cool. I just wanted to thank you first for this entire lecture. I think it's been really cross-disciplinary, and I think your lack of respect of boundaries between domains of knowledge has really shown through in a really beautiful way. So I think you did a really excellent job of intersecting math and politics and history and just a bunch of different fields in a way that actually maintained a consistent thread, and I think that's really hard to do. And like whether or not people agree with every point that came up, I think you just have to have respect for how difficult that is and how good of a job you did. So just and then just as I just had a question for you, because you sort of opened up with this and you brought this up a couple of times. You talked about how mathematics is your religious experience, or you have a religious experience through mathematics, and part of that, the way that you arrived there was that mathematics is built on a set of certain axioms, certain things that you sort of take on faith, as you put it, and religion is arrived at through similar means of thinking. And I'm wondering if you see a fundamental distinction between the type of faith that leads you to believe in mathematics and the type of faith that leads people to believe in various religions, or if you see them in the same light.
Yeah, I'm not sure I can answer that question. Like, I guess I only have access to my own religious experience, and so I'm not really able to say like why other people believe what they believe. I think it's similar. Like, my guess is that it's basically similar. But yeah, I can't prove that. I think it's pretty similar, but not really sure. Other affirmations, questions, comments? This is the time. The floor is yours. Come grab the mic.
I actually didn't need to come up here because I have a question, but can you just go into more and expound more about like the liberatory aspects of math and what this knowledge would look like were it in the control of colonized people?
Yeah, I mean, I haven't seen that, so again, it's hard for me to say. I'm like, come ask me a question. Then I'm like, I don't know the answer to your question every time. Yeah, I mean, math. I see it as like very systematic and like logical. I mean, I'm also a communist and a Marxist, and I kind of see math and Marxism as similar in that way, in that like they relate everything as a totality. Like Marxism more as like a social totality, and math more as like a whole universal totality. Like what would it look like? I mean, yeah, I guess I see math as a source of power. Like it's, I mean, again, I think it's unfortunate who has the power in society now and what they choose to use it for. But I mean, even though I think, this capitalist society is so horrible and so messed up, like there's no denying that like some of the accomplishments, of like sending people to space. I mean, the Soviet Union did that first, but the like there's no yeah, like I don't think that all these, like I still remember hearing like a few years back, like the oil should remain in the soil. Like that's kind of like a slogan that stayed with me in terms of thinking about how to address the climate crisis. I don't know, math. Yeah, it could be used for anything. Like this is such a vague answer, such a non-answer. I don't know. I mean, there's so many old traditions of math outside of kind of the Greek-derived one that is the one that I've predominantly been educated in. Like I was mentioning Gauss earlier. There's a technique called Gaussian elimination that has to do with like matrices and solving systems of linear equations. It's named for Gauss because he did genuinely do a lot of work with it. But it's also attested in an ancient Chinese text from over 2,000 years ago called the Writings on Reckoning, and I think it's clear, like from the rich tradition of math from every part of the world. Like we spoke a little bit about some African traditions, Indigenous peoples of this hemisphere, like the Mayans especially, are noted for a really rich mathematical and astrological tradition that they used to make very accurate astronomical predictions, very far out. And yeah, I think it could really be used for anything that people wanted to use it for knowing the stars, for medicine, for astronomy. Like I think I mentioned briefly, or no, I didn't mention. I meant to mention that or maybe I didn't. Anyway, the pyramids are believed to be the oldest structure employing the golden ratio. And I think it's called the Shulba Sutras, an ancient Indian text. They use Pythagorean triples to construct right angles, which are considered sacred for worship. Yeah, I think it could really be used for anything.
In response to your question, how I see it is that also mathematics and science have been used to, control like rationality and what reality is, and that's been used against women as well. So the idea that women are irrational or are outside of like mathematics and science has been a tool of oppression, institutionalizing women or illogical. So I think it's also this tool that's been used to define like what is rational, what is real, and what is acceptable.
On a much lighter note, I'd like to comment how appropriate it is that on your podium there are 2 OpenGL books called Super Bibles.
Super. I literally didn't even look. It was just for height, like. All right. So I think if there's not a final comment, we can go ahead and just close out. Yeah, I didn't unfortunately prepare this part, but yeah, I guess I just want to maybe going back to the first comment about the lack of respect that I have for disciplinary boundaries and arbitrary divisions of knowledge. Yeah, I don't know that math would really impart any specific morality or ethics in the sense that many religions do, or at least claim to do. But yeah, I do still, again, draw inspiration and metaphor from math and also from these other traditions to live by, to live on, to live with, to live through. And yeah, I mean, I'm not sure that infinity and encryption and some of the other weird fractals or whatever it is that I talked about can really tell you like what is right, what is true, to be a prison abolitionist like me or something like that. But I do hope that at least this sense of wonder, this sense of connectedness is something that might stay with you all. I mean, I think many of you probably already felt some of that before, and I hope that maybe I shared at least one thing that you might not have known before, and that you got something out of this day and this event. And yeah, again, I really just want to thank all of you for your presence, for your time, for your attention, and just yeah. Unfortunately, the food is still not here, so I want to saw a little bit more, but maybe we can. Sorry. Oh, yeah. So again, we can just hang out. We will feed you as soon as we can. But yeah, I hope that that folks are able to just stick around and keep building community with each other for a little bit longer. Thank you all so much. Peace, love, and blessings.